Okay, Chemistry 3101. This is Chapter 14, which deals with two topics, infrared spectroscopy and mass spectrometry. And during the lecture, you're going to find out what's the difference between spectroscopy and spectrometry. Well, spectroscopy is the interaction between matter and light. So when we're talking about matter in chemistry class, we're going to be talking about molecules. So we're going to be looking at organic molecules. And you guys know that there's all different types of light, aren't there? Right? There's ultraviolet light, there's UV visible, there's infrared light, there's X-rays, there's gamma rays, there's radio waves. And you can imagine that when we look at infrared spectroscopy, we're going to be talking about infrared light. So infrared light, which falls in a band of a certain number of wavelengths. Well, going back to the concept of light, you should know from General Chemistry 1, and if you don't remember, I'm just going to refresh your memory here, that light is what we call electromagnetic radiation. It has two fields that move in mutually perpendicular planes. We have an electric field and a magnetic field, and they move in the direction of the light beam. And you can see that these electric and magnetic fields oscillate back and forth. What else do we know about light? We know that light can be thought of as waves of energy, or it can be thought of as a bundle or a packet of energy called a photon. And so we see that light has both the properties of matter and of waves, which is pretty interesting. And in your general chemistry class, you would have spent quite a bit of time talking about, you know, the wave nature of light, and then the particle nature of light discovered by Albert Einstein when he did the famous experiment for the photoelectric effect. And that's what he won the Nobel Prize for. It wasn't for E equals MC squared. Anyhow, if we think about these bundles or packets of energy that we call photons, the energy of each photon is going to be directly proportional to frequency. So let's see what we have here. We've got E, which stands for energy of our electromagnetic radiation or our light. H is Planck's constant, so Planck's, I'm probably spelling it wrong here, Planck's constant, okay, which is 6.626 times 10 to the negative 34 joules times seconds. And then here we have frequency. So frequency, which, you know, you can measure frequency in hertz. It can be in seconds to the -1, right? So again, the units of energy will be in joules. Planck's constant, as I stated, was in joules times seconds. And so if frequency is in reciprocal seconds or hertz, that means that the seconds are going to cancel out and we'd be left over with just joules for our unit of energy. Well, it says here that wavelength is inversely proportional to energy. Well, when I look at this formula, I don't get that. I see that energy is directly proportional to frequency. And so based off of what I have highlighted here, we could write that since energy is equal to H times the frequency, we could say that E is proportional to frequency. Well, how do we get that wavelength is inversely proportional to energy? I'll show you how we get that. You guys remember the formula for the speed of light, right? You should remember the formula for the speed of light. And that is that the speed of light is equal to frequency times wavelength. Right? If we have a wavelength in a meter, let's say, and a frequency in reciprocal seconds, then you have meters per second. And you should know that the speed of light is equal to around 3.00 times 10 to the power of 8 meters per second. Well, now I can take this formula and I can solve for frequency, can't I? I could say that frequency is equal to C over lambda, our wavelength, right? Wavelength, again, is lambda, okay? Well, if I take this and I plug it into here, what do I get? I get that E is equal to H times C over lambda. So now we can see that wavelength is inversely proportional to energy. Here's our energy, and here's the inverse of wavelength in that formula. So what have we got? We've got that energy is directly proportional to the frequency. So higher frequency is higher energy, lower frequency is lower energy. And we've got that shorter wavelength is going to be higher energy, and longer wavelength is going to be lower energy. All right, so if we look at the electromagnetic spectrum, if anybody here is interested in writing a standardized exam, like an MCAT exam, for example, you would need to have the electromagnetic spectrum memorized. So it's a good idea. And when I say a good idea, I'm talking like my father, you know, a good idea means you need to do it. You need to have the electromagnetic spectrum memorized. You don't have to memorize the wavelengths of all the different types of electromagnetic radiation. However, you do need to memorize the order, right? So it says increasing wavelength, increasing frequency, and you can see that these are inversely proportional to each other. But what do we know? We know that as frequency increases, we could also say, going here, we could say high energy, right? Why? Because energy was directly proportional to H times frequency. And down here, we could say low energy, right? You think about all the radio waves that are going through the air right now. I'm sure that almost everybody in the class has a cell phone, and you have radio waves that are going through your body at this moment, right? You have the waves that from any kind of telecommunications, right? These are giant waves that are moving through us, but they're low energy. But nobody says, like, don't go outside because of the radio waves. Well, no, they're moving through us at all times. Whereas if you get up to infrared, and that's what we're going to be concerned with this morning, they're a little bit shorter and they're a little bit higher energy, but still we don't fear them a whole lot. But once you get up to something that is a shorter wavelength than visible light, like UV, I'm sure you've all heard of like harmful ultraviolet rays. Why? Because they have a shorter wavelength than visible light, and they are higher energy. Then we go up to X-rays, and if you've ever had an X-ray at the dentist or doctor, you know that you have to protect yourself from X-rays. Then you get into gamma rays, which are highly dangerous, right? They can, you know, cause cancer, and they can cause mutations in DNA and stuff like that. Anyhow, something else I just want to point out to you is that if you think about the range with which the human eye can detect electromagnetic radiation, so what we can actually see, the light that we can see, going from red, orange, yellow, green, blue, violet, right? You can see that it's actually a very narrow range from 400 to 700 nanometers. This wavelength scale is not, you know, it's not to scale, right? It's a very narrow band that we can detect with our eyes. But again, what's the point of this chapter, right? The whole point is this, is that we're going to take infrared light, okay? So it's nothing more than this. We're going to take infrared light, we're going to shine it at an organic molecule, and somehow we're going to get some information about the functional group and that organic molecule. Is it an alkene? Is it an alkyne? Is it an amine? Is it a aldehyde? So on and so forth. And it sounds crazy when you first hear it, right? If you haven't taken the time to read the chapter and you just think, what, I'm just going to shine light and it's magically going to tell me the functional group? Well, not exactly. You're going to have to do a little bit of work to figure it out. But again, the idea is that we're going to use the infrared light just to be able to determine the functional groups in an organic compound. Something else that I want to point out about infrared spectroscopy, which again is going to be the major focus of this video, is that you see that infrared waves have wavelengths that range between 2 micrometers and 50 micrometers. But the actual region that we use for infrared spectroscopy is actually more like 2 to 25 micrometers. Okay, so that's the actual range that we're going to be concerned with in this class. So for spectra, we go from 2.5 micrometers to 25 micrometers. All right, well, let's keep moving here. It says that when light, the light that you shine, whether it's infrared or whatever, when light interacts with molecules, the effect is going to depend on the wavelength. So if you're wondering, if you go back to this slide here and you say, well, Mr. Dion, there's other things besides infrared light. What about X-rays, you know, and all microwaves and radio waves, you know? Could we use those for anything? Well, it depends. Different regions of the electromagnetic spectrum can be used to probe different aspects of molecular structure. Now, again, you've heard me say this 100 times already this morning, but we're going to focus on infrared spectroscopy, which uses the infrared region of the electromagnetic spectrum, and it's going to give us information about functional groups. That's why we learned functional groups earlier on in the class. We don't cover UV vis in this class, but in Organic Chemistry 1, we do cover NMR, and that is what we cover in Chapter 15. So something to look forward to there. Now, NMR uses radio waves, which are much longer waves and much lower energy. But what do those tell you? And I'm just going to kind of mention this as kind of an introduction to NMR, which we're going to spend a lot of time on later on, is that they tell you about the actual arrangement of the carbon and hydrogen atoms in a compound, which is pretty crazy when you think about it. Okay, it's a very powerful tool. But again, back to the matter of IR, and all we want to determine are functional groups in a compound. Well, let's talk a little bit more about the whole concept of matter at the macroscopic scale and the microscopic scale. So it says here that matter exhibits particle-like properties, whether it's a baseball or the wheel on a car, or something really small like a molecule. Now, if you think of classical mechanics, and if, I'm sure that many of you have studied physics, and if you haven't, don't worry about it. But on a macroscopic scale, matter appears to exhibit continuous rather than quantum behavior, right? You remember from General Chemistry 1, quantum behavior, where the energy levels of the electron in a hydrogen atom, let's say, could only exist in certain discrete levels, right? It couldn't exist in between. So if you think about the tire on a car, okay, and let's say I asked you to rotate that tire at any speed. Well, you could rationalize, well, I could spin that tire at 60, let me get a pen here. I could spin that tire at 60 miles per hour. I could spin it at 60.1 miles per hour. I could spin it at 60.11 miles per hour. I could spin it at 60.112478, 90 miles per hour. You would only be limited by the sensitivity of the instrument that's reading the speed, okay, and your ability to control, whatever is rotating the tire. You could think of rotating it at any rate or speed. Well, you need to get that out of your mind when you're thinking about molecules and quantum behavior, because instead of a spinning tire, now we're going to be thinking about the bonds in a molecule, okay? The bonds in a molecule. Now, let's say we just take any kind of bond. Let's say we have a ketone, okay, just for fun. Okay, let's say we have the carbonyl in a ketone. Well, what's interesting about this bond right here is that bond can vibrate. Now, the vibration, I know when I think of the word good vibrations, I think of the Beach Boys. But anyhow, when I think of a vibration, you think if you start your car, right, and you put your hands on top of the hood, well, you can feel it vibrating. Now, the word vibrating, the way we use it in organic chemistry is to mean that the bond is stretching back and forth, okay? And that is what creates a vibration. So on the molecular scale, now we're talking about something really small. A molecule is very small, okay? If you think of biology class in high school, and let's say you look at the cells in an onion skin or something under a microscope, the high school doesn't need to spend a whole lot of money on those microscopes because cells are big, okay? Compared to a molecule, okay? You go to a cell, then you go down to an organelle, then you go down to what organelles are made of. Well, I can tell you, my friend, that a molecule is much smaller than all these. We cannot view molecules under microscopes. So the point I'm making is that the molecular scale is so dang small that it doesn't obey the laws of classical physics. Molecules exhibit quantum behavior. It is a little strange to us, right? That's why quantum mechanics is a difficult subject, okay? If you think about, when I did a chemistry degree, I took a whole class on quantum mechanics, and I can tell you it was not an easy course, okay? But what do you need to know for organic chemistry 1 is that this bond, okay, that I have in the red circle here, it can stretch, okay, I'm using a resonance arrow improperly here, but it can stretch, to a certain size. It can stretch big or small. It can stretch, but only at certain rates, okay? And this is where it gets kind of difficult to understand, but you have to take my word for it, is that it can only stretch at certain frequencies, okay, or certain rates or certain energies, right? Now, why did I use the word frequency? Because we know that energy is directly proportional to frequency. So I could, put frequency there. But anyhow, we're talking about energy. So the idea is that you see that there are discrete energy levels at which the bond can vibrate, right? Classical mechanics would tell us that it could be here, it could be here, it could be here, it could be here, right? I could spin that, think about it. I could spin that tire at any rate I wanted to. Well, now you got to get that into your mind, and it can't happen, okay? The molecule can only vibrate at specific energy levels, right? It's the same thing as if I went back here and told you, my friend, if you're driving this car, okay, this weird car, you can only spin the tire at 60 miles per hour, 61, 62, and you're like, well, that's not true. It's going to increase the speed gradually to get to 61, then it'll increase again to get to 62, but that is not the way mechanics works at the microscopic level. Okay, so give me a thumbs up if you just follow me on the concept of quantum behavior. Quantum behavior. Only certain energy levels are allowed. All right, again, not the simplest thing, But you know what? I teach I teach general chemistry during the year. And it's funny how when you read a general chemistry textbook, and I know you all have read a general chemistry textbook at some point in your life, they'll always have some kind of examples of quanta or something that's quantized in our everyday life. Like, for example, students, right? Students in a classroom right now. I just took attendance this morning. Let's say there was, 20 people in class. I'm never going to write down there's 20.3 people. It's either 20 or 21 or 22 or 19. I'm never going to write down, hey, we had 19.45 students show up today. It was great. It's impossible. Or another example would be when a hen lays eggs. The hen doesn't lay, 2.5 eggs or 2.3 eggs. Hey, this morning I got 2.8 eggs. That 0.8 of an egg was pretty sweet. No, you either get 1, 2, or 3, right? It's quantized. Anyhow, there's also some interesting applications in music that my students have explained to me. I am not going to go into that because I am not the authority. I'm not an authority on that. But my students have explained to me what quantization means in music, which is pretty interesting. Anyhow, let's go back to these electrons in a covalent bond. We said that the vibrational energy levels are separated by gaps, right? They're quantized. Now, in order to have a vibrational excitation occur, now the vibrational excitation sounds like something really fancy, but all it means is to vibrate from a lower energy state to a higher energy state, right? A higher frequency or higher energy state. You've got to strike that bond in the molecule, or you've got to hit the bond in the molecule with the exact amount of energy needed. Okay, right? E is equal to hc over lambda. You've got to hit it with the exact wavelength in order for the energy transition to occur. Okay, you might think, well, as long as I hit it with something even higher energy, then it's going to vibrate. Nope, it's not the way that it works in quantum mechanics. You've got to hit it with the exact amount of energy needed, or the exact precise frequency, or the exact precise wavelength in order for the light to be absorbed, which is kind of interesting, okay? So then the infrared light, like I told you, it generally causes a molecular vibration, which is just like the stretching of the bond. And what's cool about this, now if you're just thinking, well, okay, you got bonds in a molecule, carbon-hydrogen bonds, a carbon-chlorine bond, a carbon-oxygen bond. Well, what's so great about these bonds is that look at this. This is where it gets wonderful. Different types of bonds are going to absorb different types of energies. Aha! So that means, what does that mean? It means that different wavelengths of light are going to cause different bonds to absorb energy. So we could make a plot of the absorbance of the energy versus the wavelengths, right? And just by looking at the type of energy that's absorbed, we can tell a little bit of information about that bond. So the energy that gets absorbed eventually gets released as heat into the atmosphere. So remember how I told you about vibrations, and I told you that in organic chemistry, what we're really talking about is stretching back and forth, okay? Stretching back and forth. So the stretching, that's what we call a vibration, okay? Right? You can think of a spring, stretching back and forth. That's going to cause a vibration, right? So a molecular bond, and you see how they have it, like the bond isn't attached by a spring, Mr. Dion. I thought it was overlap of orbitals. It is the overlap of orbitals, but a spring makes a very useful analogy in chemistry, and you're going to see why. Because a bond can stretch back and forth. So it says we have stretching vibrations. We can have what's called scissoring vibration and a twisting vibration. Let me just do Mr. Dion's animation of what these mean. Okay, I hope this doesn't show up in the thumbnail on YouTube, because I always don't like it when my face shows up on them. But the stretching, right? The stretching is exactly what you think it is. I know you all understand that, right? It's just the bond is stretching back and forth. Think about it. Some bonds are strong, so it's going to be harder to stretch them apart. Some bonds are really weak, so they're easy to stretch. Okay, we'll talk about that. Now, the whole concept of scissoring, it says an in-plane vibration. I'm going to have to back up and move my chair here. But the scissoring is like this, like if the bonds are doing this, okay, scissoring, right, just like a pair of scissors. And then it says the twisting would be like this, okay, twisting like this, and then scissoring like this, and then stretching is when the bond just stretches like that. Okay, there you go. There's my animation. And there is a cool animation, excuse me, on Wikipedia. I'm not kidding, it's on Wikipedia. And I'm going to show it to you later. So I'm just going to have to remind myself to pull it up. And it shows you a little cute, no kidding, animation of stretching and scissoring. And there's other types of vibration. But in organic chemistry 1, so when you're just learning the subject, we're going to focus mainly on stretching frequencies. So these are what we're mostly going to focus on. Will your textbook mention scissoring and twisting? A little bit. And if any of you are enrolled in the lab right now in Chemistry 3102, and I know several of you are, in that class, Mr. Geiger might talk more about things like scissoring and twisting. But in Chemistry 3101, again, we're mainly going to focus on stretching. So we're stretching a bond. The bonds absorb a certain frequency or energy or wavelength of infrared light, and that causes the stretching to occur. So remember, I told you, I kind of, what's the word I'm looking? I kind of mentioned this, in passing a couple of seconds ago, but I said that the energy that's required to cause the vibration to occur depends on the type of bond. So remember, going back to this, I'm going to keep going back to it. Energy is equal to H times frequency, or Hc over lambda, either way. But the frequency of light, or if you want to call it the wavelength of light, has to be the specific type or specific amount of, specific frequency or specific wavelength that's going to cause a specific energy transition or energy, or provide the energy necessary for the vibration to occur. Okay? Now, since we have different types of atoms involved in different bonds, they're going to absorb different amounts of energy. For example, let's say we have a bond to a carbon atom, right? Everybody here knows what a carbon is. It's the focus of the entire class. Well, we see all kinds of bonds, single bonds between carbon and hydrogen in organic chemistry. It's like you can't get away from them, right? Okay, well, that's cool. Well, if you have a bond between a carbon and an oxygen, like in an alcohol, let's say, well, that actually has, or takes less energy to cause that vibration to occur. It actually takes more energy to vibrate a carbon-hydrogen bond than it does to vibrate a carbon-oxygen bond. Now, if you're asking me why would it take, less energy to cause the carbon-oxygen bond to vibrate than the carbon-hydrogen bond? But we're going to look at a formula that will help us explain why that is. Okay? But again, in order to cause the vibration to occur, you've got to hit it with the exact correct frequency or wavelength of light. It's got to have the exact amount of energy in order to cause this transition, this vibration to occur. All right, well, let's back up a little bit. So now I want you to take a deep breath like this. Okay, good enough. There we go. So we're going to take a deep breath, and I'm just going to explain what a spectrometer is to you quickly. Hey, if any of you are into those crime shows, there used to be a show called CSI. I don't even know if it's on the air anymore. You guys might be able to educate me on that. But I do know that the show, The Forensic Files, talks about like different murder cases and crimes that have occurred and things. Now that's in reruns, but in those kind of crime shows, what's cool about those when you're a chemist is that spectroscopy will come up, and spectrometry shows up in those programs quite a bit. So how we run in infrared spectrum, if you are in the lab at UCCS, if you're taking, well, I guess you're not on campus right now, but maybe in the fall, if you're taking an organic 2 with me, let's say, or the lab with me or something, or whatever class, you might see me in the hall, you could ask me, hey, Mr. Dion, could you show me an infrared spectrometer? And I can, okay? We have 2 of them at UCCS that look just like this. Now, when I was where you are back in 1995, taking an infrared spectrum was a big pain, okay? It was a huge pain because preparing the samples was very difficult. You had to prepare them on sodium chloride plates. And so it says most commonly the samples are deposited on the sodium chloride plate. Not true anymore, my friends. This is 2021. We have much better ways of running infrared spectra. So the way that they're run now is you literally just put the molecule on top of a lens. Like you just take, like let's say it's a solid, you just put a little bit of the solid on top of the lens. If it's a liquid, you would put a drop on top of it. And then what happens is the spectrophotometer, which is the name of the instrument, irradiates the samples with all frequencies of infrared light. So it's not like it scans it or something. It just shines every wavelength from 2.5 micrometers to 25 micrometers, shines it with every wavelength. And then we plot the frequencies that get absorbed. Okay? So you don't even have to worry about this whole thing about sodium chloride plates or KBr pellets, potassium bromide pellets. That's more the old way. We have much better ways of doing it now. But anyhow, let's get into the whole idea of what a spectrum looks like. So here's an infrared absorption spectrum. And if you're wondering, why do you call it an absorption spectrum? It's because the molecule, certain bonds in that molecule are absorbing infrared light, aren't they? So what's the plot? The plot is percent transmittance. So that means the amount of light that can get through. So light gets through, think it's transmitted through, as a function of frequency. And the peaks are called absorption bands. Now, if you're like, Mr. Dion, I see the word frequency here. You said you're plotting it against frequency, but I don't even see the word frequency on the spectrum. Okay, all I see is this wave number thing. Yeah, there's a good reason for that. Wave number, for wave number, we use nu with a line over top of it, and it is equal to the frequency divided by the speed of light, which is the same thing as 1 over the wavelength. Anyhow, I'm not going to stress about that with my students a whole lot. All you need to know, yeah, I'll get into what you need to know, what's most important about that. But that's what wave number is. Anyhow, so we have these peaks, and we call these absorption bands. So let me go with you really quickly here to show you what's going on. So let's say we're at 4,000 reciprocal centimeters. And again, this is the wave number, which is equal to the frequency divided by the speed of light, right? Speed of light doesn't change. Okay, it's a constant in a vacuum. Anyhow, so if we hit it with 4,000 reciprocal centimeters, or that's our wave number, that's our frequency, you can see that most of the light actually goes through, right? Because this is percent transmittance. So most of it actually went all the way through. But then if you hit it with, let's say, 3,400 reciprocal centimeters, you see that there's a huge absorbance, right? Because if it's only, around 10% transmitted, what does that mean? That means that this is an absorbance. It means that this here is an absorbance, right? Anything, right, that's pointing down like this, anything coming down like that, those are absorbances, or we call them absorption bands, okay? You're probably going to hear me call them peaks because you can see that I struggle saying absorption bands, but that's the whole idea here. So again, going into the whole concept of wave number. So wave number is equal to the frequency divided by the speed of light, right? Frequency divided by frequency over the speed of light. So what's the relationship between energy and wave number? Well, if wave number is directly proportional to frequency, and we know that energy is directly proportional to frequency, what does that mean? That means that when we have a high wave number, we have high energy, and when we have a low wave number, we have a low energy. Anyhow, I actually have a video posted to my YouTube channel that talks about where wave number comes from, and I explain, how we get from wave number, or how we get wave number from wavelength. And so I'm not going to go over that right now, but I will post a link to that video in an announcement. Again, it's not even covered in our textbook, so I'm not going to ask any questions about it. But if you're wondering, how do I get from here, there, from wavelength, I go into that in some detail in that video. All right, anyhow, there we go. So a signal on the infrared spectrum has 3 important characteristics. Okay, so let's say we're looking at a peak, like this one right here. There's 3 important things about it. We have the wave number. Now I'm just going to take the part where it's absorbing the most infrared light. So the wave number here is about 3,400 reciprocal centimeters. The intensity. So in terms of the intensity, for intensity, we have strong absorption, medium absorption, so strong, medium, and weak absorptions. The strong ones, the cutoff is going to be like down here. So I'd say that anything below here is going to be strong. Anything below 50%, I'd say that's medium. And, anything that's just like poking down like this, that's really weak. That's a very weak absorption. Now, we also have the shape that we can take into account. Now, the shape can either be sharp or it can be broad. You can see that what I have in the red oval here is kind of broad, right? If you look at all the different absorptions here, it's kind of the most broad. And if you're like, well, this is kind of broad too. Yeah, it's broad, but it's weak. So who knows if it's even all that important. But you see how if you look at this absorption here, it's much more sharp. Okay, so we have sharp and we have broad. And again, you can get information from all of these, from the wave number, from the intensity, and from the shape. So let's get into it. This is section 14.3, and this is where we really get into looking at wave numbers of our absorptions and seeing if we can get some important information from those wave numbers. So again, the frequency or wave number And again, the reason we can use those words, together is because we know that wave number is equal to frequency divided by the speed of light. So since speed of light is a constant, you see that wave number and frequency are directly proportional to one another. That's why we can say the frequency or the wave number. So the frequency or wave number for a stretching vibration depends on two different things. Remember earlier on, I showed you that if you have a carbon-hydrogen bond, let's say, versus a carbon-oxygen bond, remember that I showed you the energy gap here was really big and the energy gap here was smaller? Why is that? Okay, it depends on two things. It depends on the bond strength, so the actual strength of the bond, the interaction, the sigma bond between the carbon and the hydrogen versus the carbon and the oxygen, and the mass difference between the atoms. Well, holy heck, there's definitely a difference in mass, right? The mass of carbon is about 12 AMU. The mass of the hydrogen is about 1. Here we have the carbon, which is 12, but now you have an oxygen, which weighs about 16, right? And I got those from the periodic table. So here is the formula that you need to know, okay? And you don't have to necessarily memorize this formula. I don't think it's a bad idea to do it, but you don't have to necessarily memorize it. Let me show you what you really need to know. Okay, it says that wave number, which again was on the x-axis of our infrared spectrum, is equal to 1 over 2 times pi times the speed of light. Okay, that's a constant. This is never going to change. This is constant, right? Pi doesn't change. The speed of light doesn't change. But over here we have the square root. Remember, the power to a half is the same thing as the square root of f divided by the reduced mass. So m red means reduced mass. Now what's F? F is related to, or F is the force constant, which is the same thing as the bond strength. Now, if you remember, if anybody here has studied physics, and this is just for those people, if you're wondering what the force constant, like a spring's force constant, which is derived from Hooke's law, which is F is equal to kx, okay, where F is force, k is the spring constant, and x is the amount that the spring extends. It's like the same kind of thing. Now, if you've never studied physics before, don't worry about that. All it means is the strength of the bond. So watch carefully. It says here that if the force constant, which is bond strength, if it's in the numerator, right, that means that wave number is going to be directly proportional to bond strength. I guess I should use a lowercase f to be consistent with there. Okay, so it's going to be directly proportional. So that means the stronger the bond, the higher the wave number. The weaker the bond, the lower the wave number. Okay, and that's summarized down here. It says stronger bond, higher stretching frequency, right? Higher wave number. Okay. Well, what about the reduced mass? The reduced mass, and again, this is, if you've ever studied physics, you've probably worked with a reduced mass before. A reduced mass is equal to the product of the masses divided by the sum of the masses. So if you had the carbon-hydrogen bond, it would be 12 divided by 13. If you have the carbon-oxygen bond, it would be 12 times 16 divided by 28, 12 plus 16, okay? But if you do the math with reduced masses, and since reduced mass is in the denominator, what do you see? You see that the smaller the atoms, the higher the stretching frequency is going to be. Okay, so what does that mean? Since we saw that the carbon-hydrogen bond had a higher stretching frequency, right? It had a bigger energy gap between the stretching energy levels. It's a result of the smaller atoms, right? Because hydrogen is the smallest atom in the periodic table. Now, if you're not 100% sure about what I'm talking about, you're like, Mr. Dion, this just looks like a bunch of squiggles on a page to me. Well, hold on, let's slow down, okay? What's the main takeaway message from this, okay? The main takeaway message is that wave number is going to be equal to a constant, okay, multiplied by the square root of the force constant divided by the reduced mass. Since the force constant is in the numerator, what does that mean? The higher the F, the higher the wave number. F is related to bond strength. So the stronger the bond, the higher the wave number, the higher the frequency, the higher the energy. Okay? Reduced mass, you should know what reduced mass is. So you should memorize that reduced mass is equal to the product of the masses divided by the sum of the masses. What I showed you, or what I told you, is that the higher the masses are in the bonds, okay, since the reduced mass is in the denominator, what does that mean? It means that bigger atoms are going to have lower stretching frequencies, or put another way, the smaller the atoms are, the higher the stretching frequency. Okay? Give me a thumbs up if you're even like 80% of the way with me on this. And you're like, you know what? I might have to read this again because I would totally expect that you might need to do that. But I have another slide where I'm going to try to clear up even more of this. And if you're really ahead of me, if you read the book and you're like, I get it, just move on, get to the good stuff, okay? Well, I want to make sure that we're solid on the background before I just start, hacking my way through spectra with my students, okay? So let's look at one more slide, which deals with bond strength and bond length. Okay, so first, let's go in reverse order here. So down here, point 2, this deals with bond strength. So this here, we're talking about bond strength, right? You guys remember this from the first chapter. What did we say? As you go from a single to a double to a triple bond, what happens? They get stronger and stronger and stronger. So if bond strength is increasing, right, strongest bond, and I'm just looking at the carbon-nitrogen bonds, weakest bond, what did I say? The bond strength is related to the force constant. So the stronger the bond, right? Triple bond is stronger than a single. So since wave number is directly proportional to force constant, what does that mean? Higher wave number for a stronger bond, okay? Now with the bond masses, it's not as intuitive usually for students, okay? But that's what we're dealing with here, okay? This is bond mass, or sorry, mass of atoms in bond, that's what I should say. Masses of atoms in bonds, right? What's constant in all 4 of these bonds? There's a carbon in each one of them. If we go from a hydrogen, which weighs about 1 atomic mass unit, to a deuterium, which is about 2 atomic mass units, to an oxygen, which is 16 atomic mass units, to a chlorine, which is roughly 35, okay? What's happening? As we increase the mass of the atom, what's going to happen? Okay, it's going to affect the reduced mass, and since it's in the denominator, we're going to get a bigger and bigger reduced mass. Okay, and as the denominator gets bigger, what happens to the wave number? It's going to decrease. Nothing more than that. So again, the take-home message is, as the masses of the atoms get bigger and bigger and bigger, and they get heavier and heavier, okay, what's going to happen? The wave number is going to get smaller and smaller. Okay, so that's me basically rehashing the same thing that I did on the last slide. Okay, give me a thumbs up if that helps a little bit. Or stop me if you have a question. Okay, we're just talking about the relationship between bond strength and the masses of atoms and bonds and the wave number that's going to result in that's going to produce an absorption. Okay, kind of just, I'm sort of, as an instructor, I obviously know the subject. It's my job, right? It's my job to know what I'm talking about. And kind of what I'm doing here is spinning my wheels a little bit, kind of repeating the same thing over and over. Why? Because I've taught the class long enough to know that it kind of bears repeating when you're first, when you're first learning it. Okay, thanks, Jessica. I'm glad you guys are following me on this, because now I want to just take a look at a spectrum, right? We said that wave number is on the x-axis of our spectrum, and it ranges from 4,000 to 400 reciprocal centimeters, right? So this is going to be, high energy. This is going to be low energy, right? High wave number, so high wave number, low wave number down here. And again, we said it's related to bond strength and the mass of the atoms in the bond. Why? Because again, we know that wave number is equal to 1 over 2 pi times the speed of light multiplied by the square root of the force constant divided by the reduced mass, like that. So we can actually take a look at the spectrum, and we can divide it up into specific regions that represent specific types of bonds. For example, if we're just thinking about bond strength, single bonds are going to be way down at the bottom, right? Like let's say we have a carbon-carbon single bond, or a carbon-nitrogen, or a carbon-oxygen single bonds. Those are going to absorb at low frequencies or low energies, or they're going to absorb at low wave numbers. Why? Because they're weak bonds. Then once you get up to double bonds, they're going to be in the range of 16 to 1850, let's say, or 1875, something like that, or 1900 even. Why? Because they're stronger. And then you get up to triple bonds, which are going to absorb at even higher wave numbers. Why? Because they're stronger. Now, here's one that will throw you for a loop a little bit until you just think about it for a split second. If you look at bonds to hydrogen, you're like, Well, come on, Mr. Dion. A hydrogen atom can only ever form one bond. You just told me that all the single bonds are down here. Okay? Why the hell, pardon my language, would a bond to hydrogen absorb at such a high frequency? Why would the energy gap be so big? Why does the absorbance occur at such a high wave number? Can anybody answer me or give me like even a 2-word answer as to why? Could anybody give me a really simple answer as to why bonds to hydrogen would be way the heck up here and not down here? And I'm not looking for a difficult answer. There you go. Thanks, Mackenzie. Couldn't have answered it better myself, right? Allison, same thing. It just said because hydrogen's the smallest element, right? Absolutely. That's all it's got to do with it. So basically, the reason why bonds to hydrogen show up at such high wave numbers, it's kind of, you don't even think about the reduced, or sorry, it's not because of the bond strength. It doesn't really even come into play a whole heck of a lot. It's mostly because of the reduced mass, right? Because hydrogen is just so small. It's only has a mass of 1. So since your denominator is so small, it has a very little effect on the wave number. And there you go. So that's it. It's just based off of the mass of the atoms. Okay, there you go. So that's kind of cool, huh? Very cool when you think about it. All right, and that helps me, you know, the fact that you can answer that question, and a couple of my students were able to answer that question, and a couple of students gave them thumbs up, like, yep, I get it. What does that tell me? It tells me that my students understand, you know, what's going on, and they understand the gist of this formula, okay? Again, it's a good idea to memorize it. I mean, even if you just remembered this, okay? If you just remembered wave number is directly proportional to the square root of that'll get you through everything that I'm going to ask you on a quiz about the relationship between wave number, bond strength, and the mass of the atoms in a bond. That's it, my friends, okay? So let me tell you some interesting things about wave number. Let's continue on with that whole concept of wave number. Again, you saw how the spectrum is divided up, you know, go all the way from 4,000 to 400. First of all, you notice that the scale, that it isn't divided up equally, is it, right? You notice that the gap between wave number, you know, the increments are much bigger here than they are up here, okay? And there's a reason for that. The reason is that once you get down to lower wave number, we call this the fingerprint region, and we have to kind of stretch it out a little bit in order for us to really discern what's going on in the fingerprint region, and I'll show you why in the next slide. But above 1,500 reciprocal centimeters, we call this the diagnostic region, okay? Let me tell you this, my friends. Let me give you some good news. Students like good news. Chem 3101, you're probably going to be up here like 90% of the time, okay? You're going to be in the diagnostic region, and I'm going to show you why in a second. But the bottom line is that the diagnostic region provides clear information, okay? It's where, you guys know the expression, the low-hanging fruit, okay? Well, the low-hanging fruit, my friends, is all in the diagnostic region. The fingerprint is just like what it sounds like. Has anybody ever seen a video of somebody like a forensic scientist analyzing fingerprints? What are they doing? They have a magnifying glass and they're poring over everything and making notes, you know, in one fingerprint. Well, fingerprints are tough to tell apart. You know, it actually is a skill, you know, and if you're like, well, every person has different fingerprints. Yeah, but they're not that different, okay? They're actually hard to tell. You know, if I was to look at your fingers and my fingers just with the naked eye, I wouldn't be able to tell the difference, right? Be pretty tough. Anyhow, so the reason that we don't spend a lot of time in the fingerprint region in Chemistry 3101 is, you know, simply this. When you're just learning, it's difficult to analyze. Let me show you why, okay? Here's 2 alcohols, 2-butanol and 2-propanol. So this one here, I know we haven't done alcohol nomenclature, but this is 2-butanol, and this is 2-propanol. This is rubbing alcohol here, anyhow. But if you look at these 2 alcohols, remember I told you, what's the whole point of infrared spectroscopy? It's to determine, you know, to evaluate functional groups. Well, they both have an alcohol, so that's the only functional group there is. But if you look at the diagnostic region, or sorry, if you look at the fingerprint region is what I wanted to talk to you about. Okay. If you look at the infrared spectra up here and up here in the diagnostic region, it looks to me like they're almost identical. Okay. And if you're like, well, come on, Mr. Dion, there's some differences. Come on. Look, you got 2 little nubs here. Here, the nubs are in different places. Yeah, I know. There's small differences, but not big differences, right? They both have this big lump here. They both have something around here, around 3,000. So it's actually pretty difficult to tell them apart just by looking at the diagnostic region. So if you had two alcohols like this, then you'd have to get into the fingerprint region. Look at the region below 1,500. Look at this, and look at this. You can see it's very different between the two of them. Very different, okay? But I'm not going to ask you a lot of questions where I would expect you to be able to discern between two alcohols that are this similar. I could ask a question about it, but I might provide some more information if I was to do something like that. Okay, kind of cool. You know, when I first immigrated to the United States, I was working in Big Pharma up in Boulder, and I worked with a guy who was an expert in infrared spectroscopy. Now, I know a lot. I've been doing it for 25 years or something, but this guy was a real bona fide expert, you know, like one of the best, you know, infrared spectroscopists in the country. And it was just so interesting talking to this guy. And we'd look at different molecules that we were trying to determine the structures of, and he'd get into all the nitty gritty in the fingerprint spectrum. It was a lot of fun. I learned a lot of things from that guy. Anyhow, let's take a look at this one here. I know you're all going to follow me on this, right? Because you guys all understand, okay, even if you don't have the formula memorized, you know the wave number is equal to 1 over 2 pi times the speed of light. Sick of this formula yet? Multiplied by the square root of the force constant divided by the reduced mass. Okay, what does that mean? If you look at all of these carbon-hydrogen bonds, right, what are we comparing here? We've got a carbon-hydrogen bond, another one, and another one. But we see that the hybridization of the carbons are different, right? If you go from an sp3 to an sp2 to an sp, you could actually discern, you can actually differentiate between an alkane, right, an alkene, and an alkyne using infrared spectroscopy. How would you do that? Well, it's based off of the bond strength, right? You guys remember that an sp3 hybridized orbital is bigger than an sp2, which is bigger than an sp. So since the sp is the smallest, it has the strongest carbon-hydrogen bond. I talked about this with you in chapter 1. So since if we draw a line like this, let's say, we'll say strongest bond, okay? So if the bond is the strongest, the one between the sp hybridized carbon and the hydrogen, what's it going to do? It's going to absorb at a higher wave number. Pretty cool, huh? Really, if you think about it, if you just take a step back for a second, and I know that you're all learning the subject, but if you think about infrared spectroscopy, one of the coolest things about it is that you don't destroy the sample, okay? If any of you have ever learned anything or seen a show where they talk about mass spectrometry, which we're going to talk about in the second half of this chapter, mass spectrometry is a very powerful tool. It's really wonderful. It's probably the spectroscopic technique that I've used the most in my lifetime. However, and there's no big major problem with mass spec, but one of the pitfalls is that you destroy the sample. Okay, once you've run this mass spectrum, the sample is gone. Okay, it's gone to sample heaven. Okay, what's so wonderful about infrared spectroscopy is once you run the infrared spectrum, you can just take the compound right back. If you just put it on top of a lens, you just scrape it off or, you know, take it off and you still have the compound. You don't destroy it, okay? Which is really cool about infrared spectroscopy. Anyhow, there we go. Give me a thumbs up if you follow me on what's going on here. That we're just talking about the relationship between wave number and the strength of bond, and we're relating it to the hybridization of a carbon in an sp3 hybridized carbon-hydrogen bond, sp2, sp. Great. Thanks, Jonathan. Awesome. That's great. Good. All right. I know I might be going over this a little heavy, but I want to make sure you follow me. So look, if you look at these numbers, 2,900, 3,100, and 3,300, what we do, what all organic chemists do, we usually draw a line in the spectrum right around 3,000 reciprocal centimeters. Let me show you why, okay? Because in organic chemistry, you have sp3 hybridized carbon-hydrogen bonds in not every molecule that you're going to look at in organic chemistry, but come on, man. Most molecules that we look at in organic chemistry, you know, 90% of them have some sp3 hybridized carbon-hydrogen bonds. And so in an infrared spectrum, if you just go back, let me prove it to you. Look, 2,900-ish, right? It says around 2,900. Let's go back and look at these spectra that we saw. Here's 2,900. I'll just zoom in here. All right, this is 2,900 right here, peaks. Let's go to this one here. This is 2,900 here, peaks. Let's go back to some other spectrum that probably we weren't even given any information about. Look, same thing here. This is, pardon me, this is 2900. Look, peaks. So they're not in every spectrum, right? If you just ran a purely aromatic compound, it wouldn't have them. But you see those signals in almost everything, okay? Whereas, hey, sp2 hybridized carbon-hydrogen bonds and sp hybridized carbon-hydrogen bonds, they're a little less common in organic chemistry, okay? So what we like to do as organic chemists is when I print out a spectrum, and I don't recommend doing this in your textbook if you have a hard copy of the book, but if you like to print the book out or you like to print my slides out, and I will post some problems to Canvas for you to work on, what I recommend doing is literally grabbing your ruler, okay, and you put it on the spectrum like this, like that, and then you draw a line, just like that red line at 3000. And that just kind of is a good baseline to start. How do I get rid of the ruler? There we go. Because any alkyl carbon-hydrogen bond is going to be just below 3000, whereas things that might be a little more interesting are going to be above 3000, right? Look at this. We have an absorbance here at around what? If this is 3100, come on. If this is 3100, that's pretty darn close to it. So that probably indicates that we have an sp2 hybridized carbon-hydrogen bond. Look here. This is 32. This is, let's say, 33 would be right around here. Walla walla bing bang. We've got an sp hybridized carbon-hydrogen bond. So we know that we've got an alkene and an alkyne just by drawing that line at 3000 reciprocal centimeters. All right.